All right. So now that you've taken a look at what regular expressions are, and we formally defined them when we saw a couple of examples of them, in fact, the example that we just saw in the previous video showed how powerful they are. Let's actually talk about something that might sound quite um, um, surprising, and that is the fact that the regular expressions and finite automaton are effectively the same. They are equivalent in their descriptive powers. You might think that finite automaton are limited in that they can't remember much, and that they are very finite in terms of the amount of memory that they take, and the kinds of things that they can distinguish, and effectively they're regular languages. And that the last example we saw showed quite a complicated pattern that can be described by regular expressions, and it might sound these two things, finite automaton and regular expression, may sound different rather. But any regular expression can be converted into a finite automaton that recognizes the language that the regular expression describes, and vice versa. Any finite automaton recognizes a regular language that can be described by an equivalent regular expression. And so here we have a very important theorem then that would empower us to effectively design finite automata off of regular expressions and come up with regular expressions that describe languages of the finite automata. And the theorem here, which is theorem 1.54, states that a language is regular if and only if some regular expression describes it. If you look at this theorem and try to find out what it actually represents, is that it actually is a bidirectional implication. It and that bidirectional implication is effectively this if and only if statement, that you can effectively replace it with a bidirectional implication. So what this means is that it's effectively two statements combined in one. It has two directions, the if direction and the only if direction. So the statement can be broken down into these two separate statements, and we use these two separate statements and we prove them as two separate lemmas. And remember, we talk about lemmas and theorems and corollaries and stuff like that. So a theorem is a very fundamental mathematical statement, and if you wanted to get to that mathematical statement, you may need to prove some ideas before you get to it, and those ideas are kind of small theorems in their own rights, and so those we call them lemmas. So to prove the theorem 1.54, we effectively prove each of the directions is a separate lemma. So the if direction states that if a language is described by a regular expression, then that language is regular. And then the only if direction states the other direction of this statement. It says that if a language is regular, then it can be described, or it is described, by a regular expression. So basically each of the directions, the forward direction and reverse direction, are going to be represented with these separate lemmas. So we're going to actually look at the first statement, the lemma 1.55, that if a language is described by a regular expression, then it is regular. We're going to prove that because that's the simplest direction in this statement, in this theorem, and we'll see, as a result of proving that theorem, we will come up with a conversion method with a mechanism to convert regular expressions to finite automaton. And then we come back to the only if direction and prove that that's a more complicated version or direction of this theorem. And when we are done with that proof, then we will be able to actually get a mechanism, design a mechanism that takes a deterministic finite automaton and then turns it into a regular expression. So let's take a look at lemma 1.55, the if direction. If a language is described by a regular expression, then that language is regular. The idea here is that if a language is described by a regular expression, then we should be able to convert that regular expression into a finite automaton. And if we do convert the expression into a finite automaton, and we know that a finite automaton recognizes regular languages by definition, then that language must be regular. So we will basically start out with the regular expression, and we describe how we can convert this regular expression into a non-deterministic finite automaton. To do this, we are going to actually go ahead and start out from the definition. So from the definition, we know that a regular expression is defined as an expression that contains a single alphabet letter, or the empty string, or the empty set. And also that if two regular expressions are indeed, if two expressions are regular expressions, the union is a regular expression, and their concatenation is a regular expression, and their star is a regular expression. So we are going to show how to convert each of these items in the definition of a regular language, a regular expression, to an equivalent finite automaton, an NFA, and then when we're done, then we can recursively apply this mechanism over and over again to come up with the final construction of the automaton. So how does this first operation look like? If R, the regular expression, is a single letter in the alphabet, so this conversion effectively means that you have an NFA that has a start state. It reads a symbol, and then it goes to the accept state to accept that symbol. So it has a Q sub 0 and a Q sub 1, and so this is also an NFA. Let's call it N sub A. So easily we show that a single letter regular expression can be converted into a non-deterministic finite automaton. So we know that the language of R here is the set A, and we know that the language of this finite non-deterministic finite automaton N sub A is going to be also set A. Therefore, these two are equivalent. And now the last thing that is left for me to do is to write down the actual definition of N sub A. So N sub A by definition is a 5-tuple composed of set Q sub 0, Q sub 1. The alphabet, we'll call it sigma, whatever that is, and then a delta, and Q sub 0 is the start state, and the set Q sub 1 is the accept state. And then the delta basically is a transition function that goes from Q sub 0 over reading A, it goes to Q sub 1. And that's it. This machine, N sub A, recognizes the language that is described by the regular expression. So that's the first step of my proof. The second step of my proof is to show that there is an N sub epsilon that recognizes the language of regular expression equal epsilon. So the language of regular expression here, epsilon, is effectively the set composed of the empty string. And you already know what kind of automaton recognizes it. The automaton with a single start state, which is also the accept state. So we call this Q sub 0, and we call this N sub epsilon. So the language of N sub epsilon also is the empty string. And N sub epsilon is formally defined then as the set Q sub 0, sigma, delta, Q sub 0, and set Q sub 0 for the accept states. And delta of Q sub 0 and A is equal to phi. This finite automaton doesn't have any outgoing states, so the delta will be empty for any state and any outgoing alphabet or incoming or reading alphabet. Actually, for the first state also, we would have to also say that for q sub 0 and any letter, your phi, which is also q sub 1 and any letter. So there's only one transition for the first language. For the second language, there is no transitions. Okay, how about phi? What's going to happen if your regular expression is the empty set? The language of the regular expression empty set is also empty set. It doesn't recognize any language. So the finite automaton here, let's call it n sub phi, is going to be a non-deterministic finite automaton with a start state and no accept state. So the language of this n sub phi is also empty set. It doesn't recognize any string, therefore it's an empty set. So by definition then, n sub phi is defined as a 5-tuple. Q sub 0 set Q sub 0 is the set of its states, sigma, delta, Q sub 0, and the empty set is your set of accept states. You don't have any accept states, and the delta again here, delta of Q in any letter is going to be phi. So there's one state that doesn't have any outgoing transitions, and it recognizes the empty set. Okay, so we build our base cases of the finite automaton for the two languages. So how are we going to now prove the others? So what we're going to do is then we are going to prove each of these operations. Effectively, I'm going to invoke the closure properties of union, concatenation, and star. So if I'm given a regular expression that is the union of two other expressions, what I'm going to do is I'm going to, for each case, start with the epsilon, a, and phi expressions within unions, and then build finite automaton off of those, then combine these NFAs with the theorems, the closure theorems that we had. So with, let me just look them up, the numbers. So the closure of union was theorem 145. So theorem 1.45 for union, 1.47 for concatenation, and I believe it was 49, if I'm not mistaken. Yeah, 1.49 for star. And then you repeat this over and over again until the final NFA. And this completes our proof. So effectively, this proof, as you see, since the definition was a recursive definition, the proof becomes a recursive proof as well, or inductive proof as well, since the definition was inductive. So we build an NFA that recognizes R equal A, we built an NFA that recognizes R equal epsilon, and we build an NFA that recognizes the language of R equal phi. Then if your language was made of a bunch of concatenations, stars, and unions, you're going to basically use the definitions from the first three options for each of the elements in the language, and then you combine them by the appropriate closure property constructions that we did earlier. couple of units, actually in the last unit, in unit 7, for building NFAs for union, NFAs for concatenations, and NFAs for the star operation. And this will build and construct our NFA that recognizes the same language as the language of the regular language that the regular expression describes. So let's take a look at an example. I would like to now utilize the proof of the theorem 1.54 to construct an NFA that recognizes this regular expression, AB union with A star. Okay? So how are we going to do that? So this is my regular expression. The regular expression R is parentheses A B union A star. Okay. So notice that this regular expression is made of letters, of course, in the alphabet, and each of these are combined with I have a concatenation here, a union here, and a star operation. So effectively I have a concatenation here, a union here, and a star operation. So I'm going to start with each of the inner letters here, use the construction for the epsilon, phi, and letter A to build the appropriate NFAs, and then use the constructions of union, concatenations, and star that we did earlier in the last unit to build on them. So if I have R sub 1 equal A, then what would be the regular the NFA that recognizes it? So an NFA that recognizes A is going to look something similar to this. There's going to be a start state, and then with A it's going to go to the accept state. So I did that for letter A. And then for letter B, then if R sub 2 is equal to letter B, then with the same token I'm going to have a regular expression, or rather a finite automaton, just like this, that recognizes it. Okay, so this is the n sub A, and this is n sub B. Then so from these, then I can do the concatenation. So the concatenation of R sub 3 being A concatenated with B, which is this part of my expression. How does that look like? The concatenation was basically something like this. You've got your two languages. So this is the first NFA. This is your second NFA. Just put them one after another, right? So here's we got A, and then oops, and then the B, right? And then in the concatenation, remember, all I needed to do was basically to remove the accept state of my first part, first NFA, and then have all of the accept states, and then have them transition over epsilons to the start state of my second NFA. So this is my first NFA, n sub A. This is the second NFA, n sub B. And all I did is that I removed this accept state of the first one, and I had that transition into the start state of my second one. So this is the language that recognizes this. This is the NFA that recognizes A concatenated with B. Okay, so I've done that. So now, what would be the fourth description? The regular expression B. The fourth regular expression is R sub 3 union with R sub 1, right? Because this is the letter A. So the R sub 4 is effectively R sub 3, which is a concatenation up there, union with R sub 1, which is the guy here. So how does that look like? So the NFA, so effectively what I need to do is to have an NFA, N sub A, and N sub A concatenated B, and then use those to combine with the union construction, right? So N sub A was something like this. I've got the start state and its accept state. And so this is my N sub A, which is that. And then N sub and then N sub AB would be this guy, right? Here. So you've got this, which goes with an A, with an epsilon, and with a B, and sub AB. And then the construction for the union effectively requires me to add a new start state and then have that transition with epsilon to the start states of each of the machines. So this becomes my N sub A B U A, okay, which basically is the union of two NFAs, and the first NFA recognizes A, the second NFA recognizes B, and this thing is an epsilon here. These guys are also epsilons. So that's N A B U A. So finally, the regular expression R is basically R4 star, right? So what that means is that if I have my R4, which is this NUAB, so you basically have your N. So you basically have your NUAB, and all you need to do is to basically add a new start state to it, and then have each of your accept states transition back, and then you basically have your own start state here, and then you'll have each of these accept states to basically transition back to over epsilons, right? So this is how you do star. So how am I going to do that then? So the N of AUB, it has the start state and then two accept states like that. Oops, make it a little bit neater. So this is my N of A sub ABUA. So with epsilon transition, I'm going to go there, and then with an A, I'm going to go there, and then with A and epsilon here and a B. So this is my N of ABUA, and to make that into a star, what I'm going to do is I'm going to actually build a third, an input state, a new start state, make that into an accept state, and then make all of the accept states transition to the original start state over epsilon transitions. This is going to be an epsilon transition there, and an epsilon transition there. So then finally, just to draw it a little bit more clearly, then the final NFA that would recognize basically the string R, or the strings of the language that is described by R, is going to look like this, and it will have a start state which is an accept state, and it will transition into the start state of NABUA, and from there it's going to transition to NA and N of AB, which would look something like that. And then all of these are going to transition back, all of the accept states from there are going to transition back with epsilon transitions to the original start state, and this will be then the N that recognizes R. Okay, so this shows a construction of your finite automaton NFAs that recognize languages that are described by regular expressions. So that's one example, and we'll do another example shortly. Okay, now let's do another conversion for building an NFA that recognizes the language described by this expression R to be A U B star concatenated with A B A. So basically this is a finite automaton that recognizes all the strings that end with A B A, and it could have any number of other letters starting it. So how do we do this? The construction again would be fairly straightforward. We would look at each of these elements and build them, and then combine the expressions that we build with the union, concatenation, and effectively star operations. So we start with, let's call this R sub 1 and R sub 2. Okay, so then we have R sub 1 is the language or the expression A, and as you saw earlier, it'll be a two-state finite automaton. It's going to look something like this, and so it's going to have one transition and two states. And with the same token, then R sub B is going to be a two-state automaton. So R sub 1, actually let's call this R sub 2 because I call this R sub 2. You know, actually let's do them with the letters. So we'll say R sub A and R sub B. So this is R sub A, and so that's that, and then R sub B, that's that. And then, so then R sub A U B is going to be finite automaton that has a start state, transitions to R sub A, and then transitions with the epsilon to R sub B. Okay, so that would be your R A U B. And then R sub A U B star will be an automaton that will have a start state that's also an accept state, and then you would have your other transitions there. These are epsilons. That goes with an A, that goes with a B, and then all of these accept states are going to transition to the start state, the previous start state, with an epsilon transition. So this will be the automaton that recognizes A, U, B star. Then how about R of A, B, A? It's basically the concatenations of the three automaton, R sub A, R sub B, and another R sub A, right? So this is an R sub A, this is an R sub B, and this is an R sub A. And then remember, with the concatenation, all I need to do is just to change the accept states of the intermediary automaton just to irregular states, and then have them transition with epsilon to the start state of the next. And then finally, now the R sub A U B star A B A will be a machine that combines these two in concatenation. So you have A U B star, and then you concatenate that with A B A, right? So let's see how that's done. So for the concatenation, I'm going to actually try to be a little bit more clear in drawing this so that we will avoid any confusion. So I'm just basically here drawing my original automaton. So this first automaton is the automaton that recognizes my ABA. I'm basically copying that from up there. Right, so this is the R of ABA. I'm just going to put the arrows. Or I'm sorry, this is the R of AUB star. So with epsilon transitions, epsilon transition there, epsilon transition there, epsilon transition there, epsilon transition there, and then an A there, and then a B there. Okay, so this is the R of the actually non-deterministic of AUB star. It recognizes that part. And then the ABA star was a machine like this. How many states does it have? 2, 4, 6. 2, 4, 5, and 6. And so it's going to look like that. So this is going to be A with epsilon, B with epsilon A. So now this is then the non-deterministic automaton that takes ABA. And so all I need to do is to use concatenation construction. Concatenation construction here. And so what does the concatenation construction do? It takes all of the accept states of the original machine, transition them with epsilon transitions into the start states of the second machine, and then remove the accept states of the first machine. So we'll remove the accept state, each accept state, right? And then what we're going to do is that we are going to then transition it with epsilon to the start state of the second machine. We'll do this for every single accept state of our original machine, our original first machine here. So I'm going to remove the accept state here, and then I'm going to transition that epsilon transition. And then I'm going to remove the accept state here and build an epsilon transition for it to the start states of my second machine. Okay. Just to be a little bit more clean in my drawings, so there wouldn't be any confusion there. And so these will be now my new non-accept states for the first machine, right? So this is now the overall machine that is built to recognize the languages that are described by this regular expression R equal A union B star ABA. So this is effectively, as you see, a very nice mechanism, a very nice means for us to construct non-deterministic finite automaton based on regular expressions. Of course, as you can see here, this NFA can be simplified quite a lot. And so basically the first portion of this will be, you can simplify it with just one state that loops back to itself. So it's going to be something like this. that loops back into itself, and that at that point it also has the option of transitioning into the second part of the machine, right? So, the idea here is that you have a mechanism to build NFAs off of regular languages, and you can basically go ahead and proceed to simplify your machines, or leave them as they are, and then even when you're finished with your NFA, you can transition and convert it into a DFA if you wish. But this effectively completes our proof, and a bunch of examples, a couple of examples at least, that show how you can convert regular expressions to finite automata. And since finite automaton recognize regular languages, then the language, so if a language is described by a regular expression, then that language is a regular language. This brings us to the other part of our proof, lemma 1.60, that states a language is regular, or rather, if a language is regular, then a regular expression describes it. We'll do that in the next video.